outside on this gorgeous day. If you know, you know. As the summer comes to a close, we celebrate our 31 esteemed undergraduates working in groundbreaking research and summer program at CLASSE, that's Cornell Laboratory for Accelerator-Based Sciences and Education. Here with me today, I've got Carl Smolenski, our executive producer, to tell you a little bit more about what the CMS group does.
Hi, I'm the U.S. Systems Engineer for the upgrade of CMS. CMS is one of the 4 major detectors that's installed at LHC. The LHC, or Large Hadron Collider, is a 27 kilometers in circumference accelerator, the largest in the world, where collisions of protons are used to explore the basic building blocks of matter. The team here at Cornell focuses on upgrading multiple portions of the CMS detector, but the group that I work in works on the inner tracker, or the part closest to the beam pipe, where we get our first peek at the particles as they come from the collisions within the accelerator.
The CMS group works on creating these structures called Ds. They're named that way because they look like a D. On these structures, there are 11 modules on one side and 16 on the other. These right now are heaters, not modules, but eventually they'll be fully populated with modules. These modules are silicon sensors that sense when a particle passes through them and sends that information back to get analyzed through these wires. Now, when making a D like this, you have to be worried about 2 things: radiation and high temperatures. The radiation caused by the collision will degrade materials over time, so we have to use radiation-harm materials such as carbon fiber, carbon foam, and PEEK. The high temperatures are caused by the modules running and collecting data and overheating. So in order to manage this, we have a cooling tube, which you can see coming out of the top right here, in the middle in a flower pattern to cover the full area, that's sending 2-phase carbon dioxide through the tube and collecting all the heat and sending it by boiling the carbon dioxide. Now the glue that puts all these pieces together also has to be radiation hard and thermally conductive. So we use diamond doped epoxy and a similar material also to secure the modules to the D. A lot of undergraduates have to work on this project, so let's see what some of them are up to right now. So, Timo, can you tell us what you're working on for the CMS group?
Oh, so you want to know about the gantry? Come here. Gantry is a complex device that executes G-code paths. For example, this flower pattern inside the D, it executes the epoxy deposition inside the flower pattern shape. We can generate the new shapes on the gantry and execute them within the same day. After all is said and done, we've assembled 2 half-Ds along with carbon fiber. We've placed the titanium tubing inside that circulates CO2 inside the D. And we have this, the completed sealed D with the tubing inside.
And what about you, Jillian? What are you working on?
So, since Timo told you all about the D structure, let me tell you about module testing. So first of all, there are 2 different types of modules that are going to be potentially going on the D structure. There's a digital module, which only has a readout chip and a high-density integrated circuit. Now, we can still read out information, but this is not the priority module that's going to go in the D structure. We want a sensor module, which has the readout chip, the HDI, and the silicone sensor. Now, basically what happens is there are pixels that are going to be interacting with particles. The particles hit the pixels. That signal gets sent over to the DAC system that we have set up over here, and based on what tests that we're running, that information gets processed and analyzed and will be loaded onto our computer. Now the whole point of module testing is we want to make sure that all these modules work perfectly before they get installed in the D structure. If we have one faulty module on the D structure, then we can't use the entire thing. We have to replace all of those modules. So it's super essential that these modules are handled with care, and there's a proper procedure to make sure that none of them are broken, and that we know that all of them are being tested. Now, we have 2 different systems that we're working with. We have a cooling block set up. It's just a cold block powered up by the chiller, but what I specifically did this summer is I wanted to see if the module behaves differently in different set temperatures. So I set up this whole cold box system where you put either type of module in the cold box, and through a Windows program, it sends signals to the electronics box. Electronics box sends signals to a component called the Peltier. Now, Peltier is a component where it gets hot on one side, cold on the other, and when you send power over to it, it speeds up the heat transfer and sucks all the heat out of the cold side onto the hot side. So with that, we can manually set the temperature to Peltier, and we can run all different kinds of tests on that computer to see if the function is different or not. That's about it.
Embedded cooling systems in the CMS detector need to be of low mass. This is because higher atomic number materials contain larger and more quantity of nuclei that may interact with the particle data collisions and cause some interference. That's why we're very interested in developing newer carbon fiber tubing that replaces the current metal tubing in the CMS detector. This is some of the work. In the process of manufacturing these types of tubes, we use disc molds to corrugate the carbon fiber into the desired shape. After doing some vacuum bagging treatment, we get this result. This is a prototype carbon fiber plaquette. But as we all know, theory will only take you so far. So we're conducting a pressure test on the sample I created of carbon fiber tube. We're basically connecting it to the helium gas pump and slowly ramping up the pressure. We want to be able to see for leaks, and we want to record at the point of pressure where it kind of ruptures. In this little experiment, the carbon fiber prototype is being submerged in a vat of liquid nitrogen. Temperatures here can reach as low as negative 196 Celsius. This test is very important because we want to see that the plaquette can actually withstand low temperatures that are very normal inside embedded cooling systems in detectors.
Impressive, but that's not all. One of our most critical student workers takes charge of all the 3D printing that's required to run our experiments. If you listen, you can hear him hard at work right now. Score!
17 to 38.
Here back at the studio, we have Manfredo, who's working on a new coolant system. Can you tell us more about that?
Yeah, so basically as particle accelerators and detectors get more advanced, we need stronger coolants to be able to protect against the hot electronics as well as the radiation coming from particle collisions. An important concept to keep in mind is something called thermal runaway. Basically what happens is that the radiation damages the silicon sensors, breaks their crystal lattice, it creates more current. More current causes the temperature to rise, which in turn creates more current, and so you get a positive feedback loop in which the temperatures are controllable. So right now we're using something called evaporative CO2, it's two-phase. We basically get all the energy from the heat and boil liquid CO2. However, my specific job is to be investigating liquid nitrogen as a possible future coolant. One of our goals is to get from negative 20 degrees Celsius all the way down to negative 50. I'm trying different options. We're trying gaseous nitrogen, two-phase nitrogen, liquid nitrogen. One of the benefits of liquid nitrogen as well is the fact that it's a very common refrigerant in today's refrigeration systems. If you like, I can show you the setup downstairs.
Yeah, let's go.
So if you check out our system over here, we have about a 58 centimeter tube, 4 Kapton heaters, about 1 watt each. We have our chiller box, which will cool the nitrogen coming in and out. It's about negative 23 degrees. That'll cool the nitrogen gas to about 0 degrees Celsius. We got our first thermocouple reader here. It should read 0. That's how we know it's working. Travels through the tube. This second thermocouple will read the nitrogen after it has passed through the warmers. We also have these two devices right here, a pressure gauge and a mass flow meter. Those will help us with the calculations later on. A lot of math here. Then we have the IR camera here, which will be reading the surface temperature of these Kapton heaters. We can then calculate how much heat is being exposed into the air. All this is being read over here onto this system. If you notice, this is our pressure versus time graph, and we have the temperature versus time graph right there. So I finished running nitrogen through the tube, and I got some interesting results. So I finished running nitrogen through the tube, and I found that nitrogen gas is not the best coolant. If you can tell right here, we had an inlet temperature of about 13.8, outlet temperature of 19.5. That's about like a 5 degree difference, 6 degrees difference. And that was about enough to absorb 0.8 watts out of 4. So if you notice in this chart, this first heater got cooled down pretty well, but then these next 3 heaters didn't cool down at all. There are better coolants. Actually, I'm gonna send it to Rami, who can explain a little bit about what he's doing with helium.
All right. So for my experiment, instead of running nitrogen through our tubes, we are going to be using these bad boys filled up with some helium to flow through tubes with Kapton heaters, and then eventually with some carbon foam inside. And as you can see, we can adjust the pressure through these nozzles here. And then with our pressure sensor, we're going to be measuring inlet and outlet pressures. And hopefully we can do some more runs with different mass flows thanks to this. And we're going to see if the helium can cool down our heaters a little bit better than nitrogen. And just from some preliminary testing, we saw that we were able to get the helium down to negative 11.5 degrees Celsius at the same conditions as Manfredo's experiment. So hopefully that's going to show some good results. So what we're doing right now is we're basically conducting a pressure control test, kind of. So without any of the heaters on, but with gas flowing, since we only have one pressure sensor right now, we're trying to figure out what pressure is the sensor reading depending on how much pressure we're putting through using the gauge on the helium tank, because we don't know if this is perfectly accurate. And so if we can figure out what type of pressures are coming out into the tube's inlet, then while we test, we can move this over here and conduct our pressure recordings after the heaters to detect any pressure drops. This is actually the results of some of our final testing. And so as you can see here, just through some simple math, we were able to, without the foam, remove 3.5 to 4 joules per second. And then adding the foam into the tube, we were doing 5.5 watts removed from the heaters. And so considering that the heaters are giving us 4 watts of power, that's actually really good. It's good enough to cool them down, which is important because on the Pixel modules, they have these bump bonds that are very sensitive to heat. And I think I know a guy upstairs who's doing his project on that stuff, so he'll teach you more. His name's John Well.
So I am working with a simulation of bonbons. The bonbons are millimetrical white pieces that are in the module of the CMS pixel detectors. So I am working to research and explain possible problems and solutions that why the bonbons fail at a certain temperature below the negative 30 degrees. And I looking for the simulation that combines total for deformation, elastic strain, normal stress, maximum stress, to see the simulation of these bonbons. And next I will do a 4 bonbon simulation. So this is like the silicon piece that is in the module that are in the detector, and this is the indium that are pieces of indium, and this is the silicon. This is like a connector, and there is like very sensitive to temperature, and there is help to the module to detect the particles in the pixel detector.
So there you have it. The summer students have been working on amazing projects during their time here, with Jillian on module testing, Rami and Manfredo on cooling, and Miguel on tubing, and Jenuel on simulations of bump bonds. We wanted to give a special thank you and shout out to the mentors who helped these students, Schwan, Shika, Jose, Joseph, and Carl. Thank you so much for the support you've shown them over the summer. Thank you for tuning in on this beautiful sunny Ithaca day. This is Sarah Hightower.